Okay, in lecture 23, we're going to be talking about the mean recurrent time and first passage time. So we're going to define both of these in this lecture. Okay, so just to remind you of what we've already done before. So we've talked about this first return. So in a previous lecture, I introduced the notation of this f sub I to the n here. And it denoted the probability that starting in state I, the first time I return to state I is in the nth step. So remember here we have this fii to the n is basically given by this formulation where I say I start here in state I don't reach it at any time until I get to the nth step, and so that's what I mean by this fii to the n. We talked about how you could use this to talk about whether or not something's transient, because there might be a probability that you never return to the original state, or whether or not something's recurrent, then there's always the possibility of returning to that state. Okay, so given this fii to the n, we can actually say it's a distribution for a random variable tii. And basically what this tii is thought as the waiting time until the chain returns to state I. So here tii is going to be equal to n, so it takes n steps, or the waiting time to get back to the current state is n, with probability fii to the n. Okay, so given this, we can talk about what the mean recurrence time is. On average, how long does a state have to wait to return to that state? So if you start in state I, how long does it take on average to return to that state? And so this is what's called the mean recurrence time. And so basically here, that's just mu ii is the expected value of our random variable tii. And here's the formula for it. And so obviously, we're talking about the possibility that you can return to state I, so we only talk about this in terms of recurrent states. In a transient state, there's no, it may never return to state I. It could, but it may never return. So we really don't talk about this for transient states. We only talk about this for recurrent states. Okay, so notation, you can have a finite mean recurrence time or an infinite mean recurrence time. For our cases, we're really only going to be thinking about finite because we're only going to deal with finite Markov chains. However, if it is infinite, I just want to give you this idea that mu ii can be finite or infinite. So if it's finite, then the recurrent state A is said to be positive recurrent. If it's infinite, then it's said to be null recurrent. And then again, as with most of the things, if different states are in the same communication class, then they're all the same. They're either positive recurrent or all null recurrent. So we can actually define our Markov chains according to this also. So if you have an irreducible Markov chain, then the Markov chain is positive recurrent if all the states are positive recurrent. The Markov chain is null recurrent if the states are null recurrent, and if the states are transient, then the Markov chain is said to be transient. Okay, so we're also interested in first passage time. So notice what we're talking about. So let me give you the difference between what we just talked about and what we're getting ready to talk about. So here we're talking about mean recurrent time. So this is, I'm going to start in state I and I'm going to return to state I. So what's the waiting time until I get back to state I? So I get back to the same state that I started in. That's different than what we're getting ready to talk about. What we're getting ready to talk about is what's called first passage time. So this is, what's the probability that if I start in state I, then I get to a different state, state J, in the nth step. So it's the same idea, but here I'm starting in one state, and I'm thinking about what's the first time that I'm actually going to cross over into this other state, into this state J. So what's the probability that the first time that I'm going to see state J is on the nth step? I don't see it any time before that. And so here we're naturally starting in state I, so f of ij to the 0 is always going to be 0. So we assume that an irreducible Markov chain with some transition matrix P, that there is some time at which you're going to go from state I to state J if it's irreducible. So if you have an irreducible Markov chain, then we can talk about the mean first passage time. So on average, what is the expected time in which I'm going to go from state I to state j? Where here Tij, just like we talked about with Tii, some random variable with the probability of Fij to the n, that I'm basically, it's going to take me on average n steps to get to from I to j. Okay, so how do we calculate this? So again, what we want is what is the average amount of time that it's going to take, on average, to get from state I to state j. So I start in state I. What's the mean first time that I'm going to see state j? Okay, so for irreducible Markov chain, we're only going to consider irreducible Markov chains because we can talk about going from state I to state j for all of our states, right? So all of the states communicate, so we have a chance of getting from state I to state j with all of our states. Okay, so here, if we have our little schematic down here, we have I and we have our state j. And so the probability of going from I to j in one time step, we already know is this pji. So the probability we start at I, go to j in just one time step. Okay, so if we don't go to j in one time step, then we actually go someplace else. So we go to some state k in that first time step. So in order to think about this first passage time, how long does it take me to get from I to j? I can think about this as the probability that I go from I to j in the first time step, plus this probability that I don't go to j in the first time step, but instead I go to k. So the probability I go from I to k in that first time step, and then I have to think about multiplying that by this mean time that it's going to take me now to get from my state k to my state j. So I didn't go from I to j in my first time step, so I went someplace else. So my mean time is going to be, well, the probability that I would have gone here in my first time step plus the probability that I didn't go here, and then this mean time that's going to take me to get from here down to here. Okay, so how do we calculate this mean first passage time? So here, this is the formula that we just had on the previous slide, so let's kind of work with this a little bit. So I can break apart this sum here, and I can multiply it through, and so now I have the sum k goes from 1, k not equal to j to n. Then here's that, that mean time of getting from j to k after I've gone to state k on the first time step. So look at here, this is going from I to j, this is going from I to k, where k is anything else but j, so I can actually join these two together, these two sums, and say this is just the sum as k goes from 1 to n of pki. So this was the j that I was missing over here in this sum, so I just joined them together. Okay, so now remember, these sums, if I keep I fixed, the sum of all my pki's has to always sum to 1, right? So remember, think about those columns of that matrix, they always sum to 1. So now I've reduced it down to this. Okay, so now what do I do? Well, I'm going to let M be this matrix. So I'm going to calculate all the mean first passage times, so of all my states to all of my states, all at once. So here I let M be a matrix of all my mean first passage times. And I'm going to let E be a matrix of all ones. Okay, so now if I look at this, here, if I think about it, mu ji, what is this? It's equal to 1 plus this sum of my p's times my mu's. Well, I can write this as my M matrix, here my mu's, is equal to my E matrix, those with the ones, plus here I have my whole M matrix except for this diagonal, except for k not equal to j, so I have to have M minus the diagonal times my P matrix, my probability matrix here. Okay, so let's work with an example. How do we actually do this with an actual Markov chain? So this is an easy Markov chain to start off with. So here we have P, we have two states. We have the probability of going from 1 to 2 is 1, probability of going from 2 to 1 is 1. So the transition looks like this. So this is an easy one that we could actually figure out on our own. But we're going to do this using the formula. Okay, so the formula, mind you what the formula was. We have this M is equal to E plus M as the diagonal of M times P. I mean, what we're looking for is we're looking for M. What is mu1, 1, mu1, 2, mu2, 1, mu2, 2? Okay, so to remind you, this is our formula. This is what we defined our M to be. It's just our mu's. Here is our probability for our example. So now if I write this out, I have my M matrix here. So here's my M matrix. My E matrix is my 1s. I take my M minus the diagonal my M, and then I'm going to multiply it by P. So this part I can simplify. So here I take this minus its diagonal, and all I'm left with is zeros here on the diagonal, and I have my other two components on my off diagonal still there. I multiply this out a little bit farther, and here I've simplified, multiplied this matrix multiplication, done that, and then just combine it. Okay, so now I have a 2 by 2 matrix is equal to a 2 by 2 matrix. The only way that I can have these two things equal, or if the components are equal, so I'm going to start off with this mu1, 2 has to be equal to 1. That's nice for us. Mu1, 2 has to be equal to 1. So what's mu1, 1? Mu1, 1 has to be equal to 1 plus mu1, 2. Well, we already found mu1, 2 is equal to 1, so this is 2. And similarly here, I can say mu2, 1 is equal to 1. And then mu2, 2 is 1 plus mu2, 1. So I get a 2 here. Okay, so let's go back and kind of look at together with our transition diagram. So does this make sense? So the mean time it takes me to get from 1 to 2 is only one step. Yeah, that definitely makes sense, right? So how about going from 1 to 1? So, and then this is actually the first return time, right? So that would be 1, 2. There's no easier way I can get there. So the mean time to get there will be in 2 time steps. And then similarly, 2 to 1, I can get there in 1 time step. 2 to 2, I got to go twice. Okay, so just to think a little bit about the importance of this first passage time, this isn't just something somebody made up. So this is an example that is given in this paper down here, a paper by Newton and others, and they modeled the progression of lung cancer throughout the body with 50 possible sites where the cancer could spread. So they had the state space for their Markov chain had 50 states, and they estimated what the mean first passage time would be, the number of steps on average it would take the cancer to pass from the lung to every other location of the body using this model. And so they started off, they actually estimated what the probability transition matrix would look like based upon autopsy results, but actually figuring out how long it would take in general to go from the lung to other parts of the body is not something that they could actually figure out using an autopsy. And so this was, they say that this is an important baseline quantitative insight into the structure of lung cancer progression throughout the body here. So it is useful. This mean first passage time all by itself is just a useful thing as well. Okay, so the next time we're going to talk about steady state and how to figure out the steady state. We've already looked at some examples of that, and we'll figure out how to actually calculate that next time.